Hi everyone, this is Jeff Geisinger and welcome to the next version of our DIVA-for-Rhino tutorials. In this tutorial we'll be going over how to import artificial lighting fixtures and then how to run visualizations with those fixtures to evaluate their performance in the scene. Again, we will be using the reference office, which is a side-lit south-facing office located in Boston, and you can download the Rhino file for the reference office along with the video of this tutorial, and you can get that on the website below. So to begin, we will be importing artificial light fixtures or luminaires into the scene. And before we do that, I just want to go over the layers of the scene just to make sure that you have the right layer configuration. So under geometry, again, we have all the different components of the scene, and those are linked to materials that DIVA sends to the Radiance, the lighting simulation engine, in order to properly utilize the optical properties of each of the components of the scene. Last time we were using the shading for the exterior shading of our window, and we don't need that in this scene, so I'll keep that turned off. And we also had a monitor material for one of the computer monitors in our scene that we used for the glare analysis, and that actually has a sort of glow material that has its own brightness. I'll go ahead and leave that turned off, so you can turn that layer off. That way the light levels that we're evaluating will only be coming from the luminaires that we are importing and not from anything else in the scene. Good, so we again have to set a location, and I'm not going to do that in this tutorial just because I had already set it, and you can check the previous tutorials to find out the steps that you need to set the Boston climate file for this simulation. We don't need to use nodes again for this type of simulation. We're just going to be using image-based analyses, so you don't need nodes. So under materials, we do need to assign materials. Now we don't need to. Our scene is already assigned with materials from previous tutorials, so you could reference those tutorials to go over the steps to do that. But for the purposes of artificial lighting, we actually need to use this load Ies File command that's in the submenu under tutorials. And before I load anything, we actually need to locate an Ies file. We have to download one from a lighting manufacturer. And an Ies file is actually the common file standard by the Illuminating Engineering Society that they've established for photometric data for different light fixtures to be a kind of a common file format for professionals in the lighting industry to exchange. So how do we get these Ies files? Well, different lighting manufacturers actually post them along with their different products in order for designers to test the performance of different light fixtures. And so why don't we go ahead and open up our browser, and we can Google a common lighting manufacturer that has Ies files associated with their products. And I'm going to be accessing light fixtures by Zoom2Bell. Now, Zoom2Bell is an international supplier of lighting fixtures, and if we go to their website, we'll see that there's a line of products that has associated Ies files. And I would recommend clicking on not the North American site, but rather the international English language site. And that's only because the products on the international site, on this second one that is zoom2bell.com, not zoom2bell.us, the products on this site are going to be in metric or standard international units. If we go to the North American site, we might be importing products that have imperial units, and that might not appropriately transfer over into what we're going to be modeling in our reference office file, which is in meters. So again, let's just go ahead and click on the zoom2bell.com link, and that will open up the Zoom2Bell website. And you can see under the header there is a products kind of sub-tab. So I'll go ahead and click on products. And under categories, I'm interested for our space in bringing in some linear light fixtures. Those can be found here under surface mounted and pendant luminaires. So these will be luminaires that are that are either mounted to the surface of the ceilings or hanging as pendants, but that usually take on a kind of linear quality. And you'll see that that will open up a series of other choices for different types of luminaires. And I'm familiar with these fixtures, and I want to scroll down to a linear fixture that's very simple and that has LED, an LED light source, and that has different kind of configurations for its application within an office. And so I'm going to go ahead with these light lines. Again, I wanted to just put in a simple line of light, and I'm going to pick the slot light to LED. And clicking on this product will bring up some more information about the product, and you'll see that there are a couple of different choices. There's a corner fixture, and then there's two types of linear fixtures. One, and I think that they're differentiated by their degree of protection, and that just has to do with the kind of the tightness of the housing and the construction of the housing of the luminaire. And so let's just pick the basic one, the first one, the IP40. And then that brings us to some more information about the light fixture. We have some common features about the luminaire, and then some differentiating features that we can choose for our product. And you can see that it's got a nice aluminum housing and a kind of diffusing grille below. And if we scroll down, you'll see that there's a few different choices for this light fixture. I'll go ahead and just pick the first one, the simplest one. It has the PMMA stands for the light diffuser, and the 3000K is the color temperature. So I'll open that up, and based on so you see that there's a few different categories that are really organized by the power, the wattage of the fixture, ranging from 10 watts down to 74 watts. And just because I've done some experimentation with this fixture before, I'm going to go ahead and pick one that's sort of in the middle, the 39 watt fixture. And also what's differentiating about these subtypes underneath the LED light line is this category, or this component of the description here. It's a little bit confusing. It's a long description, but you'll see that it begins with slot, that's the name of the fixture, then the power, then the light source, it's an LED 830, it's an LED fixture. And then this next line item is the length of the fixture, L611, and that's the number in millimeters. And since our space is roughly, it's over 3 meters wide, I will go ahead and pick a fixture that, this 39 watt fixture has a 2.4 meter length, so that should fit nicely in our space. And then we don't really need to worry about the other features of this light fixture for our tutorial. But I'll go ahead and click on this 39 watt, 2.4 meter long fixture, and it opens up a product page that goes into a little bit more detail. It gives you an overview of the light fixture, and you'll see that it has things like the luminaire, the luminous flux of the luminaire, the efficacy of the luminaire, lumens per watts, color rendering index, and so forth. And if we go to the data sheet, you'll see that there is some more information about the housing of the fixture, which could be useful for us when we bring in the file into Rhino. It should be noted that the Ies file that we bring in, it brings in some geometry into the Rhino scene that you'll notice, but it's really just a flat plane. It's kind of like a representation of the bottom diffuser of this light fixture. It doesn't have any geometric information about the housing. And so we have to reference this information and make some assumptions about the housing to inform the way that we locate the light fixture in the scene. And I'll go into that in a little bit more detail in the subsequent steps. And if we keep scrolling down, you'll see that there is a light distribution map, which is really, it's talking about the angular spread of the luminous intensity of the fixture. And that just gives us an idea of the light spread and whether or not it's a downlight, how wide of an angle the luminous intensity spreads, and also if there is any indirect component. If there was an indirect component for this fixture, we'd see a cone that would be on the top of this, on the top half of this circular diagram. And we know this is just a downlight, so the angular spread of the luminous intensity is only pointing downward. And on the right, we see that there is some more descriptions and some downloads that we can access. And what we specifically need for our tutorial for actually running an artificial lighting analysis in DIVA is this photometric IES data. So if you hover your mouse over that and you click that, we'll actually get a download of the IES file. And I can open up this file actually because I've downloaded a software called Ies Viewer, and you could access that as well if you go to Google and you type in Ies Viewer. You'll see that the first hit is this photometricviewer.com, and that links to a free download to a software that you can install that is able to read these IES files and get photometric data using this interface. So if I go back to my Ies Viewer, you basically see that this gives you the same information about the angular spread of luminous intensity, this polar diagram that shows you the spread of this light fixture. You can also use the software to get some more information about the light fixture, but since the product website, the product information that was given to us by Zoomtobel is actually quite comprehensive, it might not be necessary to install the IES Viewer, but it's up to you. But what's important is that we did download that IES file, and it's located in our downloads folder. And so I'll go back to Rhino, and now if we go to 4 views, now we can actually insert that IES file. So by, as we saw before, opening up that sub-menu under Materials, and we go to Load IES File. Now we'll take a look at the command prompt. It's running a command called sub IES to rad, and it's basically just it's a way to get IES files into Radiance using DIVA as an interface. And that prompts a dialog box for you to select an IES file. And so I knew that I had downloaded it to my downloads folder. I click that, and here it is. This is the IES file that I just downloaded, and I will open it. And then we need to take a look at the command prompt for what to do next. It's asking us, what would you like to call this luminaire? I'll go ahead and call it slot light 39 watt, just so I remember the power of the light fixture in case I need to bring in some more. And so once I have entered the name in the command line, I hit return, and you see that it brings in a fixture in the Rhino space, and you'll see that it brings it in. If I go back to 3D view, it brings it in at the corner of our reference office. It's actually at the 0 point. If I bring in my grid and I say show grid axes, yes, you'll see that it brought it in at our 0 point, and I'll turn the grid off. So I'll hit escape. If I go back to the command line, you'll see that when it brought in the luminaire, there was a command in the command line that I overwrote. It was the luminaire geometry just created can be moved and rotated freely about the Rhino file as long as it stays on its current layer. And the mirror command does not work with IES geometry, and so that's important. As long as this IES, as this light luminaire geometry that we just imported stays on its layer, Rhino will know how to assign the proper photometric data to it. And you'll see that DIVA automatically generated a layer in Rhino to assign for that lighting geometry, and it's under a group called DIVA Luminaires that's automatically created, just the way that DIVA Thermal and DIVA Analysis Services were automatically created. And then the sublayer is actually the layer that contains the lighting fixture. And you'll see that it has the name that I assigned to the lighting fixture, slotlight _ 39 watt. And this is important that this layer stays the same name and that this light fixture stays on this layer. It's actually on this layer right now. And that's important because it's actually connected to a Radiance material that is in our Radiance material file that DIVA will use to assign the photometric data and the optical properties to that geometry that we've created. If we were to move it to another layer, then DIVA wouldn't know to assign the 39 watt IES file photometric data to that lighting geometry. So let's move the light fixture into a position that could be useful for our scene in illuminating our desks during non-daylit hours. And so I'll go ahead and rotate this fixture, and I will create a luminaire design, luminaire spacing that will hopefully work well with providing the right amount of illuminance to our scene. So I'll go ahead and center it on the space by moving its center point to the center point of the wall. And I will move the lighting fixture so that it is centered on the desks. So you see that in plan it's centered on the desks, but in section it's still actually at the floor. So I'll go ahead and move it from in the right view, move it from the floor to the wall, to the ceiling, excuse me. And now you see that it's flush with the ceiling. And if you remember from the product data, you'll see that from the housing that there's a few different ways to actually incorporate the light fixture. We can have it recessed with the ceiling, in which case I would have to create an opening in the ceiling, or maybe just lower the light, the light fixture just a tiny bit off the ceiling so that it's not coincident with the ceiling plane. You'll see that there's a surface mount option that is 100 millimeters off of the ceiling, or 110, and then there's a pendant mount option that you can hang the light fixture from a distance as long as that your cable is allowed to, that drops it from the ceiling. I'll go ahead and do the surface mount option. It could be a simple way to configure the light fixture in our space. So as you remember, the distance from our diagram was 110 millimeters, so I'll go ahead and say 0.11 meters. And that brings it to the surface mount height. And so now that I have it at the right height, I'll go ahead and copy this fixture so that it's centered on each of the desks. So I'll copy it using the corner of the desk at the base point, and I'll move it to the middle row, and then I'll move it to the end row. So here we have 3 light fixtures. If I go to perspective view, I'll zoom out, you'll see that we have 3 light fixtures in our space, and they're centered on the tables, and they're offset about 0.11 meters from the ceiling. Now let's test these light fixtures by running a perspective view from the inside of our space to see the kind of light quality within our space that these light fixtures are giving us. So in order to do that, let's go to our cameras. Now you'll remember from previous tutorials that we only have one camera set up for this tutorial, for this file, and that was to do the glare analysis. For this tutorial, we'll be creating our own camera view on the inside of the space. And the way that I usually like to do that is I start with the perspective view. And actually, let's go ahead and start with this interior view. But then let's turn on the camera diagram so that we can manipulate the view in a way that gives us a little bit more of a sense of the entire room. I don't really want to do a fisheye lens for this particular view, even though we used it for our glare analysis. I think just a normal perspective view would be good for this. So I go to I right click on the camera, on the view name, excuse me, and I go down to set camera, and then I go to show camera, or you can type in F6 to access this. So this shows the camera angle diagrammatically in Rhino, and if I go to my plan view and I select the camera source, I can actually select the node, the point that represents the camera source, and move it as if it were an object. And just being careful not to snap to anything, I hold down Alt in order to not snap to anything. I'll move that camera source back to the, let's see, back to the back of the room, and that gives us a sense of, a view of one of the fixtures. Maybe we can widen this angle a little bit, and so I've clicked on the perspective view and I go to properties without any geometry selected. I just go to properties with just the view selected, and you'll see that underneath properties under camera there's lens length, and I'll go ahead and change that to say 35. The lower the number, the wider the angle, and that widens the angle a little bit, and it gives us a second light fixture that is in the cone of vision, and I think that's okay for this test. So then it's very important to save the view. If you want to use this view in Rhino, we need to save it because we already have some saved views in the scene. If I were to run this without saving it, it would just default back to the name of the view that originally I used to set this view, which is the row 1 west, and we don't want that. We want this current view. So I'll go ahead and say save as, and I'll say I'll call this whole office. You can name it whatever you like. And so now this is whole office, that's okay. And so now we're ready to run a simulation. So I'll go ahead and left click on metrics, and it opens up our dialog box for DIVA simulation options. We're going to go to daylight images because this is an image-based, we're going to do an image-based simulation. We're just going to run a visualization from inside the scene to make sure that the light fixtures are coming in properly. So under visualization, that's correct. We want to use this visualization tab. Image quality, let's go ahead and set it to medium quality for this, for the purposes of this study. And we have been using 4 ambient bounces, so I'll go ahead and increase that to 4. I think the medium quality will help to, it'll help to ensure or reduce a little bit of the granularity of the image or any distortion. And if you'd like to have a finer image, you can also go to the high quality setting. So I'll leave it at that, and I'll change AB4 just because we've been using that in previous runs. And let's see. And then we can ignore the sky condition, and then under date and time, it defaults to September 21st at 9 a.m. Let's go ahead and change it to an hour where there would be no daylight, because we don't want to get any daylight coming in. We just want to have the light. We just want to be able to evaluate the artificial light fixtures on their own. So let's set an hour where there would be no daylight. So let's say at 10 p.m. or 22. Remember that these are in increments of 24-hour days, and so we have to put in the 22 to represent 10 p.m. And camera type, we want perspective. And select camera views, we'll go ahead and use the current perspective view. So we had adjusted these radiance parameters I mentioned before, and we can leave everything else as the default. And so I'll go ahead and run the simulation. Now this might take a few minutes, and so I'll pause the simulation while it runs. And I'll come back when it's done. Okay, so when the simulation is complete, DIVA should automatically open the simulation in WX false color, and so WX false color should pop up, and it's opening the .pic image that is generated automatically, and that's located in your local project directory. If I go ahead and I navigate to where I have my Rhino file saved, and you see that there's a local project directory that is where all of the results files are saved. So I double click on that and I go to visualizations. You'll see that there was just generated a pic file with the time of day, the time and hour of the simulation that I just ran, and the name of the file and the name of the camera. And so that's where that file is located. And the results are looking pretty good, that the light fixtures have come in correctly. We'll see that you see that there is the linear light fixture is coming in as completely white, which is good because it's the brightest light source of the scene. And you'll see that its location in the space is accurate. It's how I modeled it. And there's a little bit of fuzziness at the edges of the scene. That's because I did it on medium quality, maybe increasing or lowering the number for ambient accuracy, or improving the quality of some of the radiance parameters can reduce some of this noise. But it's good for our purposes, and you see that we're also able to click on the luminance values, not the illuminance, but the luminance values or brightness for the different components of the scene. So I'll clear those labels. And so this is how you make a visualization in DIVA utilizing artificial luminaires as light sources for your scene. Now let's try to run a different type of visualization that we can use to evaluate the actual light levels that these artificial light fixtures are producing for the space. So I'll close this and I'll go back to my 4 views. So in order to do this, we actually need to create a camera view that is looking down at our office space in plan view. It needs to be perspective view because we're going to run an image, and DIVA only runs visualizations in perspective views. There are other ways to do parallel view images, but I won't really get into that for this tutorial. But so we'll be using DIVA, so we need to keep a perspective view. And so I'll go ahead and double click on this perspective view, and I will use my mouse to situate the camera in such a way that is looking straight down on the space, and it's kind of like a plan perspective. So I will use the right mouse button to sort of, and shift to pan over and position myself in a way that looks down at the space in plan. And once you have it more or less looking the way that you want it to look, this is about right. You'll see that the camera, the cone is, the camera diagram is still on in my other views, which is okay. It's shooting straight down. That's actually necessary for what I'm going to be doing next. I could zoom in a little bit by using the zoom command, zoom dynamic, zoom in a little bit there, get a little closer. And I'll go ahead and save this view as perspective plan. And before doing anything else, I'm going to go to properties, and I just want to make sure one thing, and I want you guys to do the same. Under camera, the rotation should be 0, and I think that's important just to prevent any errors about the orientation of the camera in Radiance. So as long as you started this view from, let's say, a perspective view and you rotated it in position, I think that should be okay. It's a little bit different if you start with the top view. The top view already has a kind of default rotation to it. If we were to change this to a perspective view and then ran our simulation, it actually you'd get into some problems. So it's always good to start with a perspective view and then kind of rotate it in position. So I've saved this camera view, and now, so if I were to actually run a visualization in the way that I did before on this view, it would be a problem because I would be looking straight at the ceiling, and I wouldn't be seeing any of the light levels that are happening inside the space. If you remember before, of course, our camera was situated within the reference office, so there was no problem. But this view is from the outside, and any interior lighting would be occluded by the ceiling. And you might think, okay, well, why not just turn the ceiling or the roof layer off in the view in order to see what's going on inside the space? Well, the ceiling is actually a very important component as a reflector for the light sources to distribute the light within the space. And so by turning off the ceiling, it would defeat the purpose, and it would eliminate the role that the ceiling plays, the very important role that the ceiling plays as a reflector in the space. And so that isn't really an option. One way to do this, though, is to actually create a clipping plane, so that we tell Radiance to clip our view at a height just below the ceiling so that we could see the inside of the space but still have the ceiling kind of present within the scene as a reflector. So in order to do that, we need to just type in a very short command in our Radiance parameters in order to do that. And I'll show you guys how to do that in a second. But first we need to know where the clipping plane needs to be. So we'll go to our right view where we have the camera diagram indicated here in the right view, and we'll run a distance function. So just typing in DI to get the distance in Rhino between the camera point. So I'll left click on point, and then I'll go down to the ceiling and I'll snap at the ceiling. So perpendicular to the ceiling, it's about the distance is about 11.61 meters. If you look at the lower left of the screen, you see in the lower left, of the far lower left of the Rhino screen, we have C plane, we have an X coordinate, Y coordinate, a Z coordinate, and then a number in meters, 11.61. That's the distance that I'm actually calculating right now. So if I left click on that, you'll see in the prompt it gives me 11.61. And so the distance, if I go a little bit further, I'll just run the command again, and I'll go from that point. I'll just hover down. My guess is that the light fixtures are at about 11.72, and if I go a little further, why don't we just say 11.8 is just below the ceiling, just below the light fixtures, and that'll give us a sense of that'll clip the space, and it'll give us a kind of plan view in perspective of our work planes, and it'll allow us to evaluate the light levels on our desks. So let's say 11.8. Okay, so now if we go back to perspective plan, we want to highlight this view. This is the view that we want to run, keeping in mind that clipping plane distance. And so we type in metrics, or we left click on metrics, excuse me, and that brings up again the DIVA simulation options. And we want to still do the same type of visualization. So we have daylight images visualization. Our image quality, let's go ahead and make it medium quality again. We can keep the sky condition and the date and time the same. The camera type is perspective, and we want to use the current perspective view. And so now under radiance parameters, we'll do a couple of things. So let's change the ambient bounces again to 4. That's how we had it before. We want to make sure we use the same ambient bounce parameters. And now at the end of our parameter lines, we want to do 2 things. First, we want to actually set the clipping plane. So we need to type in a command that indicates the clipping plane. And to do that, to give you guys a little bit more of an explanation, I'll pop up my browser and I will type in Google. I'll just Google rpict. Now rpict is basically, it's the radiance, it's a kind of sub-function of radiance that it determines the visualization of a radiance simulation. So if I click on the rpict file that's on the LBNL or Lawrence Berkeley Labs website, you'll see that it gives you a kind of line-by-line description of all the different commands for radiance, for rpict, for generating a radiance picture. And so if you scroll down, what's really important just to know for this tutorial, it's these types of these view settings or these view commands. If you'll remember, the Radiance commands are just a series of arguments that begin with a dash and are followed by a couple of letters and then a variable. And so what we need to do is set a clipping plane. So if you just read through some of these different arguments, you'll see that the dash VO followed by a value is the command or the argument that sets the 4 clipping plane at a distance of val from the viewpoint. The plane will be perpendicular to the view direction for perspective and parallel view types. And so we just need to enter a value, and that value is going to be the distance from the viewpoint. And we measured that distance as 11.8. And so I'll go ahead and reduce my browser, and I will go back to the radiance parameters. And it's important to always have a space in between arguments. So I go to the last one, I'll do space, and I'll say dash VO. That's the radiance, the rpict argument, and then another space, and then I'll put in the value, 11.8. And so this is just the absolute value of the distance between my viewpoint and where I want the clipping plane to be. And so that'll allow it to be just below the light fixture. And before I run, actually, we need to do one more customization of the radiance parameters, and that is to tell Radiance to return a simulation that is return an image, a simulation image that is in lux and illuminance, as opposed to candelas per meter square or luminance. Now we want every pixel of this image to be able to give us an illuminance value, so that we can evaluate how well the light levels are at our work plane are meeting the target illuminance, which we had previously set at 300. 300 lux is usually the target illuminance for office tasks, and we used it for daylight autonomy, for daylit-based office activities, but now we're using it for artificial illumination. So we need to tell Radiance to give us an image where every pixel is a lux value as opposed to a candela per meter square value. And so to do that, we do another space, and the argument for that is I. And so we do dash I. The dash I is basically just telling Radiance to, again, just make sure that it represents the value for every pixel in our high definition image as illuminance as opposed to luminance. And so we're ready to run the simulation. We want the image size to be the same, and we can leave all the defaults the same. And so I'll go ahead and click run. And so again, this should take a few minutes, and I'll pause the simulation while it's running, and I'll be back when it's completed. So when the simulation is complete, again, DIVA will prompt WX false color to open up the image automatically in WX false color, and you'll see the resulting image is what we expected. It is a section perspective cutaway in plan view of our space with the image clipping the geometry right below the ceiling and below the light sources. So it gives us a kind of a sense of the illuminance of the light levels on the different types of on the different surfaces within the scene. And you'll see that the labels default as lux because we had told it to run illuminance as opposed to candelas per meter squared, which would be the units of luminance or brightness. So this is good that this confirms that it properly ran with units of illuminance. And if I click on the different points in the scene, you'll see that it'll give us values in lux of our fixture. And I'll click on a few more, but let's go ahead and change it to a false color. If you remember, I'll make this a little bit bigger. Let's see. If you remember from our previous tutorials where we made visualizations, you're able to kind of change a black and white image or just a normal rendering into a false color rendering by expanding the false color tab in the WX false color window. And we can leave it as color fill. We want to change the legend though. Annoyingly, WX false color, while it knows to change it to lux for the labels, it doesn't know to change the units in the legend. And so we do need to manually input the legend, the units in the legend dialog here. And next you'll see scale. It usually defaults at 1000. Since our target illuminance was 300 lux, let's go ahead and set the scale to about twice that, 600 lux. And we can leave 8 steps, and we can leave everything else the same. So let's go ahead and press convert false color in order to change this image to false color. So after a couple of seconds, you'll see that it converts the image to a false color reading, or every pixel is corresponding to a lux value, and it also has a color value now that we changed it to false color, and that's ranging from 0 to 600. So I can go ahead and click on these various portions of the scene. So like right at the edge of the table, you'll see that it's very close to 300 here, and we have over 300 lux, and so forth. So this is good. So the positioning of our light fixtures, the 39 watt fixture that is about 2.4 meters long, positioned over each desk, it satisfies pretty much our requirement of reaching the target illuminance value of 300 lux. It gets pretty close. So you can click that there. And just as a reminder, this file is located in our visualizations folder, and you'll see here the two .pic files that we created. One was the view of the whole office from the inside, and the other was a perspective and plan view. So that about wraps up this tutorial. We learned how to import Ies files in order to bring Luminaire, geometry, and photometry data into our Rhino file. And then we learned how to visualize the scene using those light fixtures as the light source. And we also learned how to do an illuminance-based image as a section cutaway in order to see how well the light is being distributed in terms of light levels inside our space. Thanks a lot, and I will be back with another tutorial for this DIVA-for-Rhino tutorial series. So thanks a lot.